it might also be that we'll be uploading this session on our YouTube channel, but this is not 100% necessary. So if you are uncomfortable, especially with the second idea that we had on using the recording, please let us know. And of course, we are not going to do that. Okay. So I see that the recording has started, and we also have other people joining. Okay, yeah, the recording has started, and I think that if this is okay for everyone, I think that we can officially kick off this session. I think that from the housekeeping point of view, we have already said everything, right? I'm going to now run you through the day. But again, please keep in mind that you can definitely ask questions. You're encouraged to do that. You can just raise your hand and ask a question. This is not a webinar, so you're absolutely free to do it. If you ask a question, just please switch on your camera if you can, because of course, this way we can have like a more direct interaction with you. So just give me 1 second to share my screen. And we can then officially kick off our day. Okay. Okay. Let me know if you can see my screen.
Yes.
Okay. Perfect. Perfect. Okay, so I'm going to very quickly run you through the agenda. This is going to be a really, really simple one. I'm going to take care of a little bit of an introduction very quickly to our project as a whole, just to have it in mind and fresh, and to do like a little bit of an introduction to the concept of the operational digital platforms, which is one of the core principles of our project, because then we're going to deep dive into the 3 different use cases of Begonia. So the use cases 1, 2, and 3. Where there are use cases where you're going to see some practical application of operational digital platforms. Okay, the 3 different use cases are going to be presented by our colleagues of Begonia, the ones that have worked the most in each of them. But again, as I said before, we also have all of our partners that can be probably the most suitable people to reply to some more technical questions, right? And then we're going to have a closing. For the ones that were not here from the beginning, I don't think that we're going to need 2 hours and a half for this session. Probably quite likely we're gonna close it sooner. And I'm also going to try to keep short my part about the ODP concept and the presentation of Begonia, even if I think it's very important for all of you to know, because this is one of the key outcomes of our project. And probably this is also quite important to be on the same page, because you will understand, I think, even better the 3 use cases that my colleagues will present later. So a little bit about Begonia, super quickly. We have just seven organizations in our project. This is very handy, from 5 different countries, 2.5 years project that is going to end in 1 month. So we started beginning of 24. This is a CSA, so as you might know, the CSA projects do not have demos inside. So this is more conceptual, everything that the European Commission asked us to do. What we needed to do, and these are our goals and impact, hopefully, is that we needed to look around in Europe and try to find interesting use cases of what could have become, after our work, operational digital platforms in the energy and transport sectors. So ideally, these ODPs that now we are going to understand what they are should have been both cross-sector and cross-border. Then what we needed to do is to conduct some feasibility studies and to filter them very much, all these use cases that we were meant to find. Then to prepare them for deployment, not at the technical level, but in any case to do all the studies that were necessary to just leave everything to another project that was supposed to take all of our work and start an actual implementation. And then, of course, offer feedback to the Commission on the use cases themselves and on the ODP concepts. So these were kind of our targets at the very beginning of the project. So in order to achieve these targets, what we did is that we divided our work in 3 main phases. At the very beginning, the exploratory study, we just looked around Europe and we tried to identify as many use cases as possible. We identified 14 use cases, okay, in the energy and transport sectors of digital platforms, let's say, that could do many different things that were hopefully cross-border and cross-sector, okay? So we found a lot of them. Then we had to filter them. So the second stage was very much about filtering. So we already had to shortlist 6 because 14 were too much. These 6, we analyzed them in detail. We conducted many different analyses from the regulatory point of view, the governance point of view, the cost-benefit analysis point of view, the technical point of view. And then, so we even developed them. We didn't just analyze them, we even developed them. But then after all this work, we also had to filter them even further. So from the 6 use cases, and based on the outcome of all the work that we did, and also based on the interactions that we had with external stakeholders, we managed to narrow them down to 3. And now these 3, we have developed them even further, and we have been piloting them, right? So this is basically about doing like proof of concepts. The 3 use cases, the 3 final use cases of Begonia are the ones that many of you selected as the core of today's session. And our colleagues will present them with further detail. But as you know, we have a use case that is called electricity customer-centric ODP. The second one is a very long name, but AI-driven ODP for the integration of electric vehicles, electric trucks, renewables in the grid. And then we have the third use case, which is the digitalization of data centers, right? That basically we are now also closing the piloting, and we're going to have also the final reporting for our final deliverables of the project. This is Begonia in a nutshell. Now, though, you have heard multiple times me saying the operational digital platforms, or ODP. This is not a very clear concept. So, and since this is one of the outcomes of our project, I would like to spend a few minutes to try to explain you what is an ODP for Begonia, right? And I'm also going to anticipate that we will very soon, probably either this week or next week, publish a paper, which is a reference document on the concept of the ODP, because we think that this is one of the outcomes, one of the very interesting outcomes of our project. So try to define what it is, how does it fit in the European digital energy and energy sector, and how does it differentiate or interface with other platforms, data spaces, et cetera, okay? So I'm going to be very quick, but I hope that this is going to be clear enough. A little bit of context. So we know that, of course, the European energy, but especially digital transition doesn't come from nowhere, right? So it's coming from very key and core challenges, such as the ones of the needs of sovereignty and security. Also, of course, the energy transition targets that are really ambitious, and the need to increase European competitiveness, right? And in order to do this, the European response has been quite clear, in the sense that, of course, Europe very often starts with regulation, but for a very good reason, because we are working in very much regulated sector. So we had like a very big, very large amount of regulatory packages that were pushing into the direction of having new solutions at every level, from a digital point of view, but also from the energy point of view, but also with financial initiatives, of course, that led the way to new solutions like data spaces, smart grids, advanced connectivity, artificial intelligence, to make essentially complex systems more observable, more predictable, and that could interact way more with each other. It is in this context that, of course, fits Begonia and fits the concept of the operational digital platforms that I'm going to introduce just now, right? So we have worked a lot on this concept and to try to differentiate it from things that already exist at the European level, right? And what we did at the end of many months of work, actually, is that we came up with a definition that is here only just summarized. And I'm going to now run you through it. And I hope that this is going to be clear enough, but of course, then we're going to further go in the concept to try to explain you the core principles. So for us, an operational digital platforms that we call ODP, of course, it is essentially a purpose-built digital infrastructure. So first of all, this is a digital infrastructure, okay, that combines physical and virtual ICT resources. This is already very different from many other digital solutions because it also integrates like physical assets possibly, even if it doesn't necessarily own them. Second point, the ODP is supposed to enable the coordinated operation of critical systems. So it doesn't necessarily apply to everything, but this is especially tailored and thought for critical systems, particularly in the energy and transport domains. Third point is that it needs to have as a core principle, as a key aspect, to be in support of European climate, digitalization, and sovereignty objectives. Then it is supposed to go beyond data sharing, essentially supporting the interoperable data flows that need to be, of course, secure, the real-time operational intelligence, and the service orchestration. So it is also very much about service orchestration, acting on the devices itself, right? And final point, but this is not less important, is that an ODP it needs to interoperate with and build on existing European digital ecosystems or infrastructures. So it's not about creating something from scratch, right? It is about integrating diverse systems and stakeholders with existing solutions in a common operational framework. So I've said a lot of words. I think that partly I've clarified the concepts, partly maybe we even made more confusion. But let's see if with the rest of the presentation, you're going to have a clear picture of what an ODP is from our point of view. First and foremost, let's start with something that probably some of you are wondering right now. So what is the difference between an ODP and a data space, right? Because the two things could be slightly confusing, even if for the ones of you that are more used to the concept already from the definition, probably you have spotted some differences. So first of all, an important distinction to be made is that ODP are designed even to interoperate with the data spaces. They're not an alternative, right? They don't compete with them. So they're actually building with them. The data spaces are very, very important for the ODPs. They're pieces of the same puzzle, but they're just different pieces, essentially. If you want, like in a nutshell, I'd like to say that a data space is asking how the data can be shared. Sorry? I know this was background noise. So a data space essentially is asking how the data can be shared securely and in an interoperable way, while an ODP is asking, or even more like answering the question, how can that data be used to coordinate and operate critical systems in real time, right? So as you can see here in this table that we see in front of us, is the primary role is very different. We have trusted data exchange for data spaces, where for an ODP is more operational coordination and service delivery. So this is about service delivery and service orchestration. The fact that the data spaces don't necessarily act on the data, not necessarily, let's say they govern them, where an ODP has to act on the data. So it has to transform them into operational value, into operational intelligence. And then the physical dimension, of course, because the ODP is, as we said before, both software and hardware, right? So, and then there are also many other differences. Now, for the sake of time, I'm not going to run you through them, but I hope that this is already clear enough. In our work on the ODPs in Begonia, and this is also very important as an introduction to what you will see in the slides that my colleagues will share with you after for the three different use cases, we have developed a layered architecture for the ODP. This is the architecture that our technical partners came up with, so we know that this is very, very solid. And as you can see, this is made by 4 main layers, okay? So that they start from the raw data collections at the bottom value to the delivery at the top, right? And the point is that the components don't all necessarily need to be owned by the platform, by the ODP itself. What is actually very important is that they're connected and compatible and governed in a proper way. So at the very bottom, we have the perception layer, which is essentially the connection to the physical world for the data collection. Then you have on top of it the middleware layer, which is essentially, let's say, the backbone of the platform, because it normalizes the data, ensures the data flow and the interoperability. On top of it, you have the service layer, where here it's essentially where the data becomes intelligence, where are the services that they can be hosted. It connects with third-party service providers and can allow like multiple actors to contribute essentially to the services of the ODP. And then eventually you have the business layer, where essentially the value of the ODP reaches the users and the external stakeholders. So it provides the dashboards, the reporting tools, etc., the financial management, and the value delivery in itself. Right. So this is in a nutshell the architecture and that Begonia came up with for the ODP. And probably you will see a bit of a reflection in the presentations of the single use cases after. Now, as you might have understood up to this point, of course, ODPs have a need to interact with a lot of different stakeholders, right? Because they can bring together a wide different range of actors. And each stakeholder can contribute in a different way. And of course, this depends very, very much on the single use case. So the stakeholders that can be involved in an ODP, of course, are use case dependent, as you can see here in this slide. So, and they can have also very different roles, depending on the use case. But of course, you can have from public authorities to infrastructure operators to market actors in case you have to interact with the electricity markets and place offers in these markets, to of course end users that are the receivers of all the services of the ODP. But as we said, this is use case dependent. As use case dependent is the governance. So but what we have done and what we have understood with the work of Begonia is that, of course, the governance follows the use case. This is very obvious, and that the appropriate model depends on the objectives of each platform, the objectives of the single use cases. And you can have like a very diverse set of possibilities. But among them, we have identified, for instance, some where we have like just a trusted centralized entity, right, that acting as a neutral platform operator. In some other cases, the best fit was to have like a distributed or a federated governance model. In other cases, you had more like public and private arrangements with, ensuring probably more legitimacy, because what matters anyway the most is to ensure the coordination and the trust, especially because, as you saw at the beginning, we are dealing with critical infrastructures. So is absolutely vital to ensure the trust among the players and to adapt the governance depending on the single use case. So we are reaching almost the end of my presentation about the ODP. Just a few hints on the design considerations, and let's just call them lessons learned about the design considerations. They're very general, but they're very general for a purpose, because you have seen before, everything is very much use case dependent, but in any case, we can find like a common connector, a common line between everything that we have been doing in Begonia with the ODPs. So first of all, our architecture, the one that we have proposed, for us, it's the one that makes most sense. Of course, it's a reference, it's not a prescription. This doesn't have to be necessarily the ODP architecture, but it's the one that it worked very, very well for our use cases. So of course, this is recommended. Second point, the ODPs needs to be designed for integration and not ownership. What we mean by that is that the components of the ODP do not, both virtual and physical, don't need to be owned or directly operated, all of them at all times by the platform. It's about also the integration of the existing one. So there can always be possible to find arrangements where you just operate something, but you don't own it directly, right? Third point, we said at the beginning, to favor always the retrofitting or the replacement, and to try to integrate and enhance existing digital solutions rather than creating new ones from scratch. Third point, I'm going to repeat myself, the government must follow the use case. And then fifth point, which is quite obvious probably for any digital system, given the pace at which technologies are advancing nowadays, the ODPs should be designed with the adaptability in mind, like thinking that, of course, this is a sector that is evolving very, very rapidly, also because of AI. So from the inception, it's very important to understand that this needs to be designed with this in mind, right? However, among the lessons learned, is very important also to highlight the challenges that we have identified with the ODPs. because the first one probably is about the European regulatory fragmentation. Many ODPs are cross-border or have to be scalable in multiple countries, and this is or can be an issue because we still have national implementation differences of European regulatory provisions. This is often due only to delay of uneven transposition of these provisions, but this does create barriers if you want to deploy them tomorrow morning, right? Second point is kind of cross-sector legal gaps. So if you have like ODPs where you have solutions that work in energy transport, for instance, energy transport digital, maybe they have like slightly different regulatory packages that have to deal with them. And sometimes this can complicate the deployment and identification even of responsibilities across sectors. Third point is the technical maturity and standardization. And here, of course, we have to talk about interoperability because interoperability frameworks are still evolving, right? Also, data spaces that are very important for the ODPs are still evolving. So sometimes, of course, we still have to make tailored integrations, and this can be a big problem today if we want to deploy ODPs in the world in which we live nowadays. And then, of course, is the governance, because the governance, this is quite obvious. We are dealing with critical infrastructures. Governance can be very tricky. And also when the ODP interacts with physical assets, sometimes it can raise the questions of liability, safety, compliance. This is solvable, but of course, this can be a challenge in some cases, right? What I can tell you, though, is that these challenges are absolutely real, and we have to be very cautious if we want to implement an ODP of everything that we see here, and even more, of course, this is just a selection of them, right? However, some of these barriers, or many of the barriers, are actually just transitional. They're not structural. Like the barriers that are related with the European regulatory fragmentation are just related to the fact that different European countries did not implement in an even way European regulatory provisions. The ODP as a concept is very much in line with the European regulation. So eventually, this should be possible to implement it from this point of view, from the regulatory point of view, in all European countries without having massive restrictions, right? And of course, if you want to like end in a positive note, also the issue of interoperability, which is very, very big, as we know, they are consolidating also the standards. So we are moving, we know that this is a problem, and we are working, many projects are working to try to solve the issue. So I think that eventually we will be able to solve it. But of course, again, nowadays, this is something that we have to be aware of. So finally, just a few final comments to wrap up my part. I think that we have demonstrated what is the concept of the ODP, and that ODPs are actually feasible, not just conceptually. It is possible to implement them, even if we want to do it today in June 2026. This is probably still tricky, but in any case, it definitely is possible, and they have like a huge potential. Second, of course, we have defined the concept, and this is replicable and even more probably scalable at the European level. We know that. Third point, as I was mentioning before, that the European landscape is moving in the right direction, not only in terms of regulation, but in terms of other projects that are all contributing to an environment that is actually very favorable for the implementation of the ODP, such, for instance, the digital spine, right? That is now becoming a bit of a hype. The ODP fits perfectly there. In fact, our colleagues also worked on a paper about this with partners from Insieme and Eclipse Digital. And finally, is that now is what needed to be done now is action, not only to continue the research and to continue the work, but just to lift the barriers that especially we have, for instance, from the regulatory clarity at the national level and more cross-sector collaboration. So this is it. I hope that at a certain level, I have clarified a bit what is that we mean by an ODP. I also encourage you to follow us, because very, very soon, as I was mentioning at the beginning, we will publish a reference document about the ODP concept that I think could be actually quite interesting for you to follow. So if anyone has any questions, of course, I don't know if I will be able to see them because I'm sharing my screen and unfortunately I don't see the chat. But if someone has any questions, please let me know. In any case, what we will do at the end of this session is that we will reach out to all of you with a little poll. This is going to just take you a couple of minutes, but for us, it's very important to gather your opinion. Of course, we will also encourage you again to ask us for follow-up questions that maybe after digestion will come more naturally to you. But that said, this is all for me. What we can do now is to pass to the first section of today's session, the deep dive into the use case 1. I'm gonna then stop sharing my screen and leave the floor to our colleague Mohsen Banai from DTU that worked a lot on the use case 1. So Mohsen, the floor is yours. And again, to everyone, please ask us questions and we will be very, very happy to answer them even during the presentation.
Just give me a second, please. Yes. Hello, everyone. Thank you, Nicola, for the very nice introduction and presentation on Begonia. I'm Mohsen Banai. I'm a tenure track researcher at Technical University of Denmark, DTU, and I present our first use case. This use case is the result of merging 3 other use cases at the first stages of Begonia project, which was one of the, and then finally became one of the final 3 use cases. The whole work of this use case was done mostly by DTU team, including me and also Konstantin Filonenko, my colleague. I was mainly responsible for the context, for the idea of the use case, and also the services. But the whole work about the infrastructure and prototyping and deployment was done by Konstantin. But I will present both 2 steps, both the idea of the use case and services, and also prototyping. But this is just for keeping a balance between presentations, because my colleague Konstantin would later also present use case 3. But he is here with us, and if in any case, if you have any technical question about prototyping and piloting, he would also be here to help us. So regarding the first use case, I will start with a short introduction. We all know what is happening for energy system. We are facing with more electrification of different sectors, including mobility and heat. And at the same time, we are having more and more investment in renewable energy sources. At the same time, we can see that all this investment has reached us to a point that we are facing with some risk power curtailment, renewable energy source power curtailment, which causes some technical and financial issues for risk providers. And at the same time, we are facing with rising issues with grids regarding the voltage regulations, congestion, and also balancing. So here, with all these issues, one of the promising solution is to engage end users to be part of the solutions. But on the other hand, the problem is that there is not much interest from end users for some reasons, including the trust, data privacy issues, and also the complexity of different solutions when it comes to deployment at building levels. And also, we are facing with privacy and regulatory compliance issues. We have different regulation at different member states. Some regulation doesn't even allow demand-side flexibility to be as part of the solutions. And also we have the regulations on data. But also at the end, when we have all the sectors and assets together to have a solution, we are facing with fragmented data and systems that cannot work together based on different standards, protocols, and interoperability issues. In this situation, we need for a secure, regulatory compliant, and also privacy preserving coordination of all the actors, assets, hardware, and software solutions, so we can achieve the objectives we have at the EU level, and also incentivize end users to be part of the solutions. In this regard, we came with the idea of the use case 1, a customer-centric ODP. Here, the idea is to propose a platform that puts put consumers or customers at the core and try to use the demand side flexibility for supporting the renewable energy sources and also the grid. The platform we propose here has some core features. The first feature is about empowering customers to contribute to green transition. We want to provide a platform, an environment for the end users, so they can trust on the procedures. They have sovereignty on their data, and they can easily be connected to the platform and provide services. Of course, the platform cannot only work with end users. We need multiple stakeholders to support the platform, including DSOs, TSOs, aggregators, tech providers, and end users, of course. And also, we try to define the use case in a way that allows both autonomous and non-autonomous or manual interaction of end users with platform. So we want to allow end users, so even if they don't have the infrastructure to connect to the platform, they can, if they are interested, they can still contribute to grid support or renewables support. And then, of course, the platform is cross-sector. We try to have some consideration about the heat sector and also mobility. We try to leverage AI for different services, including forecasting and optimization. And also, we propose a sustainable governance scheme to ensure what we develop as the platform can sustain in long term. So the platform we propose includes 4 main services: virtual energy community service, data, demand side flexibility aggregation, and of course, disaggregation service, a recommender service, and automated or semi-automated switching of energy supply. I start with our first service. So all these services together build the platform. But each service within itself include many microservices that all together makes the platform work. The first service is the virtual energy community service. As you can see here, we have a variety of services. We need to do the forecasting for building, forecasting for renewable energy sources, and also run optimization problems. But after all of this happens at building levels, we need to aggregate the flexibility, estimate flexibility for next days, and also bid it into the ancillary service market. Apart from this whole energy community, we try to maximize the self-consumption of renewables within the platform. But in any case, if we cannot support the whole demand by renewables, we need to buy electricity from the day-ahead market. And also, if we have extra production, we can sell it to the market. So that's the whole idea of the virtual energy community. We have some buildings, some controllable loads, and all together the goal is to maximize the self-consumption in the community. The second service is just about the flexibility aggregation. So here we don't have the part about maximizing the self-consumption, and the focus is just to provide balancing service to the grid. This could be not balancing in any other service, but that would just facilitate aggregation and disaggregation of flexibility from different sources inside the platform. The third service is the recommender service. This is the service I mentioned that allows end user to interact with our ODP using mobile apps. So in any case, if an end user does not have a technology at the building to connect to the platform and react automated, they can receive notifications from a service in the ODP that would tell them, okay, if it is possible to reduce their consumption or even increase in some cases. For this reason, we need to monitor the grid, forecast the vulnerabilities, and identify relevant end users that can help to solve the issue and send notifications. Of course, some of these services might be done by TSOs outside of the platform, but the platform can also allow doing this. And the last service is automated switching of supplier that would allow the end user to change their suppliers using the platform. Through the project, after defining the use case and services, we needed to do some analysis on the use case. The first analysis was about policy and regulatory analysis, which was led by Olivo Energy team. They did some analysis at EU level and also the national policies to see if the services can work at the target country and also at EU level. So many regulations and many policies, including the data protection, electricity market, the AI Act, and so on, were investigated, and to ensure that what we develop as a services and also what we deploy at the end can support the regulations and also the policies. The next step was about the governance analysis. Just like what Nicolo mentioned, we perform a comprehensive analysis on the governance, and we analyze different governance schemes that could fit within the ODPs of different use cases. To do this, we had some steps done. We analyzed the value creation and value exchange within the platform. We identified different stakeholders for each use case. For this case, you can see the end users, facilities with controllable loads, risk providers, EV owners, retailers, aggregators, DSOs, and TSOs as involved stakeholders. We identified the key concerns of each of these stakeholders. Also, we perform a cost-benefit analysis to see if the use case can sustain financially. And at the end, we came with the idea of a governance structure. But after we came with the governance structure, we of course ensure that it is aligned with the regulations. Considering all these steps, we came with an idea for a governance model. This study was done by one of our partners in the project, OASC. The final governance scheme for this use case was to have a private for-profit ownership. The operational model was to have a commercial platform offering value-added energy and flexibility services. At the governance, the idea is to have a transparent governance mechanism to build stakeholder trust and also balance the interest. And of course, as I mentioned, it would be compliance with the regulations. We have an architecture for each use case, which we will see also later in the next presentation, and also Nicolo went through it in his presentation. This architecture includes 4 main layers, starting from perception layers that reads the data from the IoT sensors, meters, and controllable loads. We have the middleware layers that manage the data and data normalization, data ingestion, and so on, and also make it possible to connect to data spaces. At the service layer, we have the core services of the platform, all what I mentioned before, AI services, automated switching of supplier, virtual energy community service, and also some other services like financial settlement services and billing services we need for assessment of providing the flexibility, and all these services, they will be in this layer. And at the end, we have the business layer that would have the visualization and also the billing. So now I'm going to go through the prototyping step. This prototyping was done by 3 of partners in the project, DTU, Semoso, and CDK. This was led mostly by DTU team, as I mentioned before, my colleague Konstantin. And I'm here just to present the main achievement of the prototyping. So, as also Nicolo mentioned before, Begonia was not aimed to have a larger scale prototyping or piloting. What we need to do is just to have a proof of concept prototyping. And for this reason, our focus for this use case was to deploy only one of the services or key services that I mentioned before, which was the virtual energy community service. But of course, the other service about like the flexibility aggregation could also come under this service. So this service can provide a very comprehensive view of the deployment and also the requirements. we need to follow. So when it comes to energy communities, an energy community is built up by some buildings, some controllable loads, some renewable energy sources, and also they can interact with other markets. They usually lack digital infrastructure, real-time monitoring capabilities, AI-based optimization tool, and secure mechanisms for data sharing. And what we did in our platform, in our proposed ODP, and during the deployment was to connect energy communities, sensors, and renewable assets to grid actors, enable sovereign and secure data exchange using the data space connectors. We provided AI-driven forecast and optimization. We also support flexibility services and self-consumption maximization within the platform, and a user-friendly platform or UI was developed so it can allow end user to interact with platform easily. The deployment was done at all 4 layers of the architecture. At the perception layer, we emulated and simulated different types of hardware. So we had this limitation. We couldn't connect to real data center or wind turbine or like this, but we simulate some of them and we emulated them on hardwares. So we have actually Raspberry Pis that includes models of these systems, batteries, wind turbines, and data centers, and can receive the data and react. The controllers also send the control signal to this Raspberry Pi. So we try to have a better demonstration when it comes to the edge devices. At the middleware layer, we deployed Kafka for data streaming and also data space connectors. As service layer, all the services we need for the virtual energy community was deployed. And also at the business layer, we came with a PTX bidding platform, a user interface for platform users to interact with services. In the rest of my presentation, I would repeat some of the few words that I just wanted to introduce them at the beginning. You will hear about the Kubernetes cluster, which is supposed to work as a operating system of the platform when it comes to the deployment. It hosts all the services that we talk about and make them running. But also we have the Kafka streaming backbone that supports the data streaming between each two device or devices and services, or between the services. And of course, we have mutual TLMS to ensure encrypt and authenticated data exchange. The prototyping was done in 4 main phases. The first phase was about the platform development and initial infrastructure. So we started working on the PTX bidding platform, which is which was developed as a full stack web application. We used React 19 for a front end deployment, and also Node.js for backend, and also to be a bridge between the data and services, and also the front end. And we built everything on the Begonia Kubernetes cloud. As you can also see here as a screenshot of the platform, you can see that the platform allows visualization of services, GIA-based map that allows to put different devices anywhere in the map. And we are also working to also put the grid on this map. So in that case, when we put the device somewhere in the map, it is also connected to the grid, and we can analyze the impact on the grid. And there are also some dashboards that you can see the real-time data streaming, what is happening in real time with all the controllable loads within the platform. We have also added some features to the platform that allows users to simulate different hardwares. For example, if you wanted to have a data center with some specific parameters, there's a tab here you can go through, adjust different parameters, and then you have a data center working, and then and also it can interact and provide services for the platform. In parallel, we also established a sovereign data exchange infrastructure using Eclipse data space connectors, and also Kafka streaming for and mutual TLS for secure data exchange. At the second phase, when we have the infrastructure ready, we work for making the data exchange to work. So the DTU will host the data from energy consumption, PV generation, and wind generation. But our partner Semosa in Spain does the forecasting service. So we use Kafka to stream the data securely between DTU and Semosa, and then the forecast from the Semosa was received again and sent again through using Kafka to also DTU for running the optimization problems and also ODP dashboard for visualization. At the third phase, we have the AI forecasting and optimization tools running. So as I said, the previous step, we had the data streaming. Now we have the services to work. So at Semosa, we do the forecasting using the data, and this forecasting is transferred to DTU for running the optimization problems based on the forecast and also the data we receive from the meter, sensors, and the devices. And then the result at the final step are sent back to Semosa for further analysis, for example, for calculating the estimated flexibility for next day, and also for the platform for visualization. Here we had some main conclusions. I just go through some of them. We noticed that what we have at the edge level. So as I mentioned before, at the edge level, we have the Raspberry Pis that run the optimization problems. And we noticed that this, like the not very powerful hardwares as Raspberry Pis can work very well and run the optimization problems and simulations very well. So we can find them as very suitable technologies to be used at the edge. Also, we validated decentralized intelligence. So ODP is not seen as like a one solution at cloud, but all the solutions are distributed at the edge at different devices level. And at the last phase, we validated the data space connectors. So we tested data space connectors in 3 different environments: VPS, Kubernetes environment, and also on Raspberry Pis at the edge, and we validated their performance. It all worked. Now I'm going to also show some screenshots of the platform. I had also some slides ready for the perception and middleware layer, but it was just like kind of repeating what I already mentioned. So at perception layer and on middleware layer, we tested all what we discussed before in my previous slide, and we validated the performance. They all functioning well. And also at the service layer, when it comes to the data management, you can see it here as like a screenshot of the platform that would allow us to have access to the data, to have a real-time streaming result and how the whole platform works. Other services we deployed are like flexibility service, self-consumption maximization service, AI forecasting service, battery optimization, market clearing service, data centers, and also real-time streaming and connecting to the data space. So regarding the forecast, our partners at Semosa did a great job with forecast, and we did the forecast on both PV panels and also the building energy consumption. Regarding the battery optimization, the platform allows you to monitor, first of all, what is happening with PV production and data and energy consumption at the building, but it also shows how the batteries would react to the price signals and also to flexibility signals to reduce the cost and also maximize the self-consumption of renewables. And here also is one of the another figures that shows how the results of flexibility capacity calculations. Sorry about the quality of figures. these are all I had access to. And then, as I said, the platform allows you to design a data center, insert different parameters of the data center, and run it and optimize its operation. So this is a screenshot where you can see that you can enter different parameters for chillers, for servers, for heat pumps, for UPS battery, for a data center, and simulate its operation as a part of the platform. We have also the clearing market service. In reality, the ODP would not have the market clearing. The market would be an external service that the ODP would connect to. But here, to show the whole functionalities and interaction with markets, our colleagues also deployed a market clearing service in the platform that could also allows us to bid into this market and also receive the prices. We emulated and simulated some of the other market players to bid into this market and all the clearing procedures of the market. The platform also allows connecting to the data space. So we have as two buttons, both in the map view and also the optimization view, that would allow the end user to easily connect, string the data with the platform using data space connectors. So this is also another tab on the optimization that you can see that still you can the end users can connect to the platform using data space connectors. Regarding the key technical outcomes, I can say that we completed edge optimization pipeline running on Raspberry Pis and MCU hardware. We tested data space connectors. We tested all the entire platform services working and running very well. Also, all the services try to use open source technologies, so we don't have a challenge in that regard. And also, we try to come with a reusable architecture plan that ensure scalability for future and can also interact with data space. As far as I know, my colleagues went through different difficulties and challenges during the deployment. One of those were about data streaming, and they finally they decided that they prefer interoperable cloud native architecture over using vendor specific solutions for data streaming. Edge devices, we noticed that we can be very meaningful devices or technologies to run AI optimization at the edge. But edge devices, I mean Raspberry Pis, of course. And then we of course we need some continuous monitoring and robust solutions so the platform can be up and running all the time. And one of the key outcomes was about the data space, that we noticed, okay, data space is a very powerful tool, but it still requires practical integration and with more validations during different projects. Thank you very much, everybody, for your attention for my presentation. In case you have any questions about the infrastructure, you can contact my colleague, Konstantin, and he would help you. Thank you, Nicolo, for the time.
Thank you. Thank you very much, Mohsen. So I'm gonna leave a little bit of time to see if someone has a question. If this is not the case, I mean, if you want to ask a question, you can just raise your hand. We're gonna see you. We're gonna leave you the floor. As I said at the beginning, we are here for that, so please do so. In that case, if not, as I mentioned at the beginning, we are gonna reach out to you with an email with a very short poll, and then you can also send us your question afterwards, after having a little bit of time to digest everything that we have been saying to you today. And we will also share the presentations that we have used during today's session, right? Since I don't see any hands raised, I think that we can pass to the second presentation of the day and to yes, we do have a question.
Yes, thank you very much, Nicolo and Monse, for the presentation. This is Ander Zubiria from Tecnalia. Just two, let's say, brief questions, one on the data acquisition and the other one on the data exchange. The first one, how did you deal with the data acquisition in the edge devices? So if I understood correctly, you are like emulating the distributed energy resources, right? So there's no connection with, let's say, the data source or the submitter or the meter, right?
I think I can answer this if
Yes,
that's
of course.
yeah. So we had two cases actually. It's not that all the device we do not connect any of the device. We actually have a battery for the first use case, which we connect directly to the platform through Kafka, and it streams real-time SOC measurements, charging, discharging, and we're displaying it on the front end. So and actually we also optimize at the same time the battery itself, the battery operation. So it's a closed loop, truly closed loop, as it should be in the ODP. I'm sorry, yeah.
No, thank you. So in this case, then the connection was through the API of the vendor of the battery in this case.
No, not through their API, but for our own API in Python. So we basically have a server running on Raspberry Pi that collects data from the battery, and at the same time collects the data from the MPC running Python. And then actually it's actually basically the coupling of the real time and the optimization algorithm and Kafka. So yeah, that happens on edge.
Okay, thank you very much. And
yeah. Sorry. I just wanted to finish about the emulator as well, because yes, we also have devices that we physically cannot prototype, but then for that ones we use simulators.
Okay. Thank you very much. Actually, very interesting this the architecture and the way that you are managing like real world, very deep technical problems. The second question was, on very simple. What's the reason behind using Kafka broker instead of other MQTT brokers like, I don't know, Mosquito, for instance?
So Kafka is more production ready and it's scalable. So we kept all our technologies in the way that they are scalable into the cloud. And the important part here was, which is mostly the focus of the use case 3, but also for use case 1, it's quite important, is the sovereign compute implementation and scaling of that compute. Because if you have a cloud managed by hyperscalers, it's easy to scale. But if you are targeting, cloud EU compute architecture, then and also edge architecture, and then combining those, then scalability becomes a problem. But for that, there are some solutions that we are exploring. So that's actually more a topic of use case 3.
Okay. Thank you very much, Konstantin, for the answers. That's all from our side. Thanks.
Okay, fantastic. Thank you very much, Ander, for the very interesting questions. If there is no one else that has a question, but of course, we can always collect them and answer to you them later. I'm very happy to leave the floor to Elena Boskor-Kovac from Blueprint Energy Solutions and for the presentation about the second use case of Begonia.
Yes, it's a pleasure to be here. Just let me know, Nicolo, can you see the screen shared?
Perfectly.
Perfect. Okay, good morning, everyone. We are advancing now into the second hour of today's workshop. Thank you for joining it. And it's my pleasure to present the use case 2 from the Begonia project with a very heavy title, an AI-driven operational digital platform designed to coordinate electric mobility, renewable energy, and electricity grids across borders. So this use case also came to fruition by merging several aspects of mobility, or we had 3 other use cases that were dealing with large-scale electric vehicles, meaning trucks. There was commute of passengers on motorways, and there was also a nudging or advisory app development for fleets or individual EV commuters as the third use case. So we tried to give it a comprehensive look, because one of the most important ideas behind projects like these, and one of the most, let's say, significant challenges to solve, address problems which are cross-border and cross-sector. And this use case truly is both cross-border, because while electricity and renewable production is predominantly a nationwide issue, unless we're counting interconnections, transport, especially heavy-duty vehicle transport, trucks transport, is inherently a cross-border aspect. And with the dawn of electric mobility, this started to pose a significant challenge on the grids. So it's simply no longer a transport issue. It's becoming a real-time operational coordination challenge between charging infrastructure, electricity grids, renewable generation, fleet operations, and mobility systems. And this challenge becomes even more complex once we look at the corridors across Europe, so electric truck corridors, high power charging, and cross-border mobility flows. For this reason, we decided to address this issue comprehensively, to try to tackle some things that have not been fully developed before, but having in mind that there has already been significant investment in EV charging across Europe. So use case 2 focused on operational coordination of electric vehicles, electric trucks, renewable energy sources, and electricity grids. The idea was predominantly generated in this condensed area when we talked to utilities, charging point operators, and operators of motorways in the region, with Austria, Hungary, and Slovenia contributing a lot. But some of you present in this workshop actually had a lot to say and are involved in EV projects yourselves. And you have noted some of the biggest challenges here, which was essentially very fragmented data. The idea was not simply to optimize individual charging stations here. The objective was to coordinate charging demand, renewable availability, and grid constraints and mobility flows together in real time. Even if we have one and the same electric truck from belonging to the same fleet crossing the border, you are well aware that in this dense area, we have very different approach to dynamic pricing, very different approach to feed-in tariffs, to where the renewables are utilized and how. Not to mention negative prices. So this really does affect charging point and challenges for the grid. Renewable production is variable, grid capacity is constrained, and mobility flows do not stop at national borders. So the challenge was coordinating this demand, renewable generation, and grid constraints dynamically across fragmented systems. It's nice, and there are a lot of studies that have been done on the impact, but the challenges are now in real time. So this is what I mentioned before, and the response or what we volunteered here is leveraging AI, and there has been a lot of AI utilization in renewable forecasting, in forecasting of flows, congestion-aware scheduling. However, we addressed the use of AI and preparation of data that also detects anomalies in transport across motorways and some lateral ways. So that's why AI is in the title, because the data essentially needs to be proofed, checked, and sometimes enriched with the use of AI. So this is opening the context a little bit more. So the use case 2 addresses one of the most pressing challenges in Europe today. How do we scale electric mobility, both passenger EVs and electric trucks, without destabilizing the grid, without creating congestion, and with maximizing renewable energy use? And the core problem is that the single motorway charging hub may experience simultaneous megawatt scale charging peaks during some traffic surges. You are well aware that even though we are in Schengen, there are often, during certain periods, massive congestion, which are a bit less of an issue when we talk about individual passenger vehicles and more of an issue when we talk about fleets. The answer is not simply adding more chargers. The answer is coordination. And single motorway charging hub can experience simultaneous megawatt scale charging peaks during these traffic surges. And then charging demand becomes volatile, renewable production is inherently variable, and grid capacity is limited. So due to the fragmented charging networks, fragmented data ownership, which I believe many of you experienced if you're working in this field, there are also fragmented market rules. So it's important to note here that sovereign data exchange becomes critical here because infrastructure operators are often reluctant to share operational data openly due to cybersecurity concerns, operational sensitivity. This is critical infrastructure, liability considerations, and that's why ODP solution with federated governance and data space approaches is actually so important. So I'll go into overview of main services of the use case 2, and I'm very happy to show you a little bit later what we effectively piloted in the same extent. So the main services, the first one would be coordinated smart charging and scheduling service. And here use case 2, talking broadly about use case, demonstrates several core platform services. The first one is coordinated smart charging and scheduling service. And the ODP validates scheduling and routing optimization logic that is capable of sometimes shifting charging timing, reducing simultaneous peak demand, improving charging availability, and aligning or trying to align charging activity with renewable production availability. And to give you an example, if congestion risk emerges at the motorway charging hub, the platform can generate optimized charging recommendations, alternative charging windows, or congestion-aware charging prioritization strategies. So the idea is not simply to charge vehicle faster, but to reduce simultaneous peak loading. And here I will mention something that we already noticed when working on this specific service is that representative multi-day data sets are really essential for reliable scheduling and forecasting performance. So it cannot stay just on the level of simulation, but actually multi-day data sets are critical. And I will talk a little bit more about this because it was addressed in our piloting. Now, talking about forecasting service, to make this orchestration possible, use case 2 relies heavily on some AI-driven forecasting services. Now, I want to mention, which I didn't mention before, apologies, is that later on for the prototyping here in BEGONIA project, in this last mile of the project, we have worked with the partner Wings from Cyprus, who will be here. They are the main technology partner who have facilitated the environment, the infrastructure, and also contributed some of their experience in preparing the data and preparing the nodes. We as Blueprint, we have worked a lot actually on previous projects, in flexibility projects with expected grid loading conditions, the renewable energy forecasts, and some congestion probability indicators for the grid. So that was the easier part of the job, I would say, here. And this is critical because in the prototyping phase with the grant contribution from Wings, we had to, on one side, match highly variable mobility demand and highly variable renewable generation. So instead of waiting for overloading conditions to occur, the prototyping later on can validate forecasting logic capable of anticipating congestion risk proactively almost, and forecasting therefore becomes the operational intelligence layer of the platform. Mentioning already the challenge, one of the challenges that we can see already here that should be resolved in future projects that will extend the piloting was difficulty of integrating heterogeneous operational data sets that originate from different charging stations, mobility systems, and infrastructure environments. And of course, one of the conclusions already from the analyzing the service is that forecasting quality, as anybody who has used AI for forecasting knows, strongly depends on operational data consistency and interoperability quality. And my colleagues have already mentioned more about interoperability. I will say a little bit more when we jump to the prototyping here. Flexibility, procurement, and activation service is particularly interesting. I have to say, when we started designing this use case, there was a lot of interest by different stakeholders, utilities, with their daughter companies or sister companies that are CPOs, to address this, because some utilities are multinational, some charging point operators and fleet operators obviously are present across different countries, and flexibility procurement rules are very different across Central Europe, where we focused on here. Not to limit the use case just to Central Europe, but this is where we observed some of the biggest discrepancies between countries. So the use case here via the platform validates coordination logic for flexibility aggregation, some congestion-aware charging adjustment, and some DSO utility operational support workflows. And if congestion conditions emerge, charging activity could be adjusted dynamically in order to reduce local grid stress, avoid simultaneous charging peaks, and improve some renewable energy utilization. And I would say this is another one. It was already a lot mentioned in the previous use case one about energy communities and flexibility aspects coming from that end. So I will jump right now to the last main service of this use case, which is alerting and anomaly management service, which I think is novel for this use case. So it involves real-time alerting and anomaly management because charging systems operate dynamically. Operators require continuous operational awareness, and the platform can monitor charging infrastructure status, congestion indicators, and some operational bottlenecks. And here, motorway data is particularly interesting. And predictive alerting can allow operators and mobility actors to identify operational risks before queue formation or overload conditions escalate. One important insight that we noted was that motorway charging hubs are especially sensitive to simultaneous arrival and queue escalation during peak traffic conditions, which are seasonal or I would say calendar dependent. And individually, as I mentioned, all of these services are valuable. There are more granular services as part of use case 2, but the real innovation of use case 2 is actually orchestration here. So forecasting, scheduling, flexibility, coordination, and alerting continuously. They interact operationally through the platform and give trust-based engagement principle to different stakeholders, which is one of the biggest obstacles to demonstrating use case like this or solving the challenges further on. So the key stakeholders, one of the most important insight here, this is not just a technology challenge, it's fundamentally coordination challenge between many independent actors here, and no single actor controls the full charging ecosystem. We have also reflected on the governance. The biggest question was who should own this platform. DSOs, TSOs, charging operators, mobility providers, fleet operators, renewable aggregators, roaming platforms, all operate independently with different priorities and operational responsibilities. And this makes interoperability and sovereign coordination essential. And the platform combines technical interoperability with federated governance principles, where stakeholders maintain control over their operational data, which otherwise would have been impossible to provide proof of concept here. And they are still participating in this coordinated optimization process. And what we also observed is that stakeholder onboarding, governance alignment, and interoperability standardization, they remain the major deployment challenges. So larger project extending from this concept needs to happen in the next phase in order to start removing these major deployment challenges on a larger scale. So now jumping from concept to reality a little bit more, we have demonstrated that AI-driven coordination is technically feasible. I should mention, just like Mohsen has mentioned before, that this proof of concept was obviously done in a more modest way in the sense that, and I will explain the phases, but wasn't large-scale multi-year deployment similar to innovation action projects. Rather, it was a demonstration of almost an MVP that combined some models, forecasted models for charging demand and grid load, with some scheduling algorithms designed to optimize charging times, minimize simultaneous peak demand, respect user constraints, and maximize renewable utilization. And you've seen this slide before. The main architecture layers of the ODP remain the same. We were merely using different layers of the ODP, specifically targeting the services that we were going to demonstrate. So at the perception layer, telemetry and operational data collected typically from charging infrastructure, mobility systems, and energy systems. At the middleware layer, Kafka streaming and data space interoperability mechanisms distribute operational events securely across the ecosystem. At the service layer, forecasting, scheduling, flexibility, process operational information, and generate optimization logic. And finally, at the business layer, stakeholders interact with the platform through operational coordination workflows. My colleagues from Wings can answer more in terms of the layers and infrastructure questions later on, as they were predominantly developing this environment. I would say one important lesson that we learned here was that maintaining interoperability across all these layers requires substantial integration effort, especially when combining heterogeneous operational systems and data sets. So this is the high-level view of use case 2. We will distribute these PowerPoints for your reading later on. I know this is a lot of information. This is just to present it a little bit better. The architecture of the use case 2 is deliberately federated. At the national level, you have charging and mobility coordinators, and you have CPOs that manage local charging infrastructure, user requests, and then we have grid operators managing grid constraints. And at the center, the data space coordinator and AI level support forecasting, interoperability, secure data exchange, and coordinated optimizations. DSOs, TSOs, they contribute grid awareness signals, while motorway operators provide input on near real-time congestions. Fleet operators and mobility actors also interact with the platform for optimized scheduling and routing. So use case 2, therefore, federates charging infrastructure, mobility systems, and grid operations into one operational coordination layer. This is compute infrastructure. I would add here that, and my colleagues can add more context here, this distributed architecture supports scalability, resilience, hopefully, and low latency. At the corridor level, centralized AI services support wider optimization across mobility flows. At the edge, local charging infrastructure can react rapidly to operational conditions. Charging telemetry flows, which in this case were in the end coming from anonymized from real stakeholders, from real actors, through Kafka streams into forecasting and scheduling services, which then generate optimized charging recommendations. So one challenge I would like to highlight here was that maintaining, again, consistency across decentralized components is absolutely critical. So what is the operational environment piloted? We use representative charging scenarios, which were derived. On one side, we envisioned electric trucks, specifically in this case, derived from Hungarian motorway and charging data sets. The first scenario data set represented a high-density motorway charging hub near Budapest with 4 150 kilowatt chargers overlapping commuter traffic and some retail activity and long-distance motorway flows that go towards predominantly Austria and further on. And the second scenario was representing a regional charging environment near Szombathely with lower throughput but higher sensitivity to queue formation because of limited charging availability around. So these scenarios allowed the platform to validate congestion-aware charging coordination that, in this case, fits under supply area of the same DSO. And as you have seen a similar example before, the operational environment that was prototyped also in the 4 phases. Phase 1 focused on federated infrastructure preparation with some cloud edge architecture setup, Kafka event streaming, interoperability framework preparation. Then in the next phase on preparing mobility data sets, renewable forecasts, charging telemetry, some grid awareness signals. Finally, phase 3 focused on validating the smart charging coordination, congestion-aware scheduling, and renewable-aware optimization logic with some flexibility workflows. In the end, phase 4, which is essentially now being finalized, focuses on validation through representative motorway and regional charging scenarios under realistic congestion conditions. So essentially, you can see already some of the screenshots here from the prototyping. This is previous 3 phases. As I mentioned, we are now finalizing the phase 4 with some screenshots from the platform. The platform continuously processes charging demand, congestion indicators, renewable availability, expected grid loading conditions. And the objective was to reduce simultaneous peak loading and avoid queue escalation, improve charging availability, and maximize use of renewables. They are obviously utilized differently on Hungarian side of the border and then on Austrian side of the border. Just to give you an example, across these 3 countries, Hungary has no dynamic pricing approach. Austria has it in full bloom. Slovenia just recently started it. That impacts both price of electricity, that impacts price of charging, philosophy behind it, and that ultimately impacts the business case for commute of fleets across borders. So instead of reacting after congestion occurred, the platform demonstrates predictive coordination capabilities capable of identifying operational bottlenecks proactively. And you can also see here some of the screenshots already from the piloting with scheduled timeline and renewables versus grid utilization. I don't know if the font is too small, but as I mentioned, we will share the screenshot of this in the PowerPoints that will be distributed. You can see charging point summary and optimization recommendations here, and input requests and scheduling mapping and results here. So This illustrates how charging activity could be shifted towards period with high renewable availability, lower grid stress, and we can see how charging requests were dynamically mapped against infrastructure constraints, availability, renewable forecasts, user charging requirements, and some expected grid conditions. So the final output of the platform was congestion-aware charging recommendations, and what use case 2 demonstrated is that electric mobility increasingly requires operational coordination between mobility systems, charging infrastructure, renewable generation, and electricity grids. I would love for us to have more time to sit down and really discuss the tales from this level of piloting, because I'm confident that we share the same challenges when it comes to even different providers of electric vehicles. You're well aware how much some providers like Tesla don't want to share data, how some data are proprietary depending on the provider, and that while there are roaming platforms for charging already established across Europe, access to data and anticipating commute of these vehicles is not as simple due to unavailability of all of the data across different manufacturers. So we have resolved that, or discussed how this could be resolved. We can go into further detail, hopefully in the final workshop that we're going to have, and in some follow-up activities from Begonia project. So I would say one of the most important insights, and I will conclude now with this, the biggest challenge was not capability of AI, it was operational coordination and access to data across fragmented mobility, charging, and energy ecosystems here. So hopefully that also gives you some food for thought for the future.
Thank you very much, Ellen. I think that this was very, very clear. I wonder if someone has any questions. Again, I don't see any hands raised. But again, I'm going to repeat myself. Of course, you're going to be able to send us your questions the moment that we will share the slides. We know that they're very, very dense, so there is like an immense amount of information to digest. So you can also take your time, take a look at the slides, and then drop us an email, and we're going to do our best to reply to your questions afterwards. Okay, so for the moment, I think that we can conclude this part about use case 2. Again, thank you so much, Elena, for your presentation. And we can then swiftly pass to our third and last segment of the day. But in any case, it's still extremely interesting. This is our final use case of the 3 final use cases of Begonia. And in order to present it, we have Konstantin Filonenko, still from DTU. And yes, Konstantin.
Yeah, sorry, I just can I have a break of 5 minutes, because I need to yeah, thanks.
Yeah, it's okay. So while we wait for Konstantin and for the last of the presentations of the day, I'm actually going to anticipate something that in any case I was going to say at the end. So if there is some of you that then has to leave at 12 sharp, because I know that some of you will have to leave at 12 sharp, probably they will not have the chance to listen to the next steps. So it's actually quite good if I do it now. So the moment that we will conclude our session today, I will send you an email with the links to where you will be able to find all the presentation that we shared today. They will be in the Begonia platform. The vast majority of you already have access. If you do not have access, we're going to give you access very easily. And there you can also find like a large repository of working document of Begonia all in one place. So this can even be convenient in case you want to even deep dive or explore some of the concepts. So you will not only have access to our presentations of today, but even to the past material and past presentations. And this is point number 1. In the same email, as I was anticipating, you will find like a little poll, but this is gonna take only a few minutes. I know that we are all very, very busy, so don't worry, this is very, very simple. But in any case, for us, it's quite interesting to have some results and a little bit of a take of what you think of all the work that we did, and how do you think that you could carry it forward, if you think that you could carry it forward, of course. In the same email, you will also find some more information about the ODP reference document that we will be publishing very, very soon, that I encourage you to read, because it kind of encompasses everything that we have been saying today, even if from the more like a high level, from a more high level point of view. In terms of next steps for Begonia as a project, right? So yes, you're going to receive this email this week. Between this week and next week, as I was saying, we will probably publish this ODP reference document. As we were saying at the beginning, as also Elena said at the end of her presentation, we will have the final webinar of Begonia, where we will present guidelines and lessons learned. So this is going to be a bit broader. Of course, we're not going to repeat the things that we did in this deep dive, of course. So I think that this can be still quite interesting to understand, also because hopefully we will also learn and know a little bit more what could be the follow-ups of Begonia and the next possible steps. This webinar, we will do it in the context of our final event of the project on the 25th of June. But in any case, you should also receive an email with more details of the way that we think to run it and how this should be shaped. The Begonia project finalization will be on the 30th of June. So again, we have exactly 30 days from today until the end of our project. And then, yeah, it might be that, of course, the concept of the ODP could be included in some future European calls. We don't have like full visibility about this, but in any case, we know that this is like a part of all the work that also the Commission is doing in the concept of the digital spine. So this will be quite relevant anyway. So this is just to give you like a quick reminder of the next steps. In any case, you're going to find everything in the email that I'm going to send you after today's session. And I don't know if in the meantime, Konstantin is back or not. No, I guess that this is still not the case. So if you want to take advantage to take like a couple of minutes in order to take a glass of water or a cup of coffee, maybe what we can do is that we can wait a few minutes, we can reconvene at 11:45, we can have like a very short break. That might be also very useful in order to take a little bit of breath after all the amount of information that we have dumped onto you. So while we wait for Konstantin, maybe let's do that. Let's wait 3 minutes. Oh no, you're back. Okay, great.
Yeah, thank you for a bit of break. I'm a bit sick, so I needed to take a cup of tea. So thanks.
No worries, no worries. So yeah, no need to stop then. I can leave the floor to you, and you can go ahead with the presentation of the final use case.
Yeah, just yes. Share my screen. Yes.
Yes, we see it, but we don't see it full screen yet.
Okay. Yeah, just a moment.
Yep.
Let's see if that works. Yes.
If you have some technical issues and you need us to share your presentations, you can also send it to me. Okay.
Right.
Yes.
Well, actually, I have some technical issues here. I'm sorry. It's a bit hectic for me today. But
no worries.
May I just ask a question before Constantine? I just noticed that some of the slides are hidden. Did you do that on purpose or?
No, that's that was in the template that I used. So that's why I now converting it to PDF so that I don't get into trouble with that. Yeah, thanks. Okay.
Reset.
Almost there.
Otherwise, Constantine, I was saying before, if you want to share it with me and I can share my screen, if this is easier.
Yes, but I think I'm done here, so I can just share my screen again.
Okay, now we see your screen.
I just need to, okay, but it's saved in the wrong way. Okay.
Okay, then maybe for the sake of time, what you can do, maybe you can avoid to use the presentation mode and you can just jump through the slides like this. Probably this is easier and faster.
Okay.
Yeah.
Yeah. So this use case considers digitalization of data centers. And I will start with the context, challenges, and solutions that this use case provides. And the main context of the use case is that digitalization of data center is ongoing now within the EU regulatory framework, and it aims for primary efficiency, flexibility provision, and waste heat reuse in terms of energy sector. And then there's in our use case, we target three countries: Denmark, Germany, and Finland, because they have a similar attitude towards the digitalization of data centers. And we have built a prototype where we have servers in Denmark and then rented servers in Germany and Finland. So we host the ones at DTU in Denmark. And apart from that, we have also we host also a digital platform that actually allows to provide services to the data center and across data centers. And then we have the AI-driven operational cycle set up. That is the main focus of the use case. And basically what we do there is we are forecasting consumption and generation in the regions where the data centers are located. And then we optimize future consumption in terms of favorable scenarios to resolve congestions. And then we do actuation of the loads accordingly, either in the same data center or across data center, and monitoring. So we also know that data centers, their primary business, of course, is not energy, but data services and operational services, hosting virtual machines, clouds, and so on. And for that, we use the sovereign data exchange connectors using IDS and Gaia X frameworks. And the key partners here are DTU, Center Denmark, Net Zero Data Centers, and Energinet. they are co-authors of the use case. But of course, the piloting was done in a smaller setting, that is primary DTU sent to Denmark, and some consultants that helped us with cloud native tools. And then this is well aligned with European strategy. I just mentioned one here, but generally it involves a lot of different. We align with a lot of different EU regulations here. Speaking about the EU framework and regulations, there are several directions to innovate data centers and digitalize them according to different strategies. Like, for instance, there's a digital strategy in the EU, and also there's some energy incentives that are taken into account in this use case. For instance, there is a issue in integrating mid-voltage data centers that are supposed to be operating at full load because there are certain capacity limits on that range. And data centers, they are very much interested in resolving that issue and being compliant with local and EU regulations concerning that. And in this use case, we address that by introducing grid services and also some kind of scheme how data centers can enter energy market. We're not prototyping the market itself, but there are some things in our platform that actually help future development of market participation schemes. So sector coupling is another important thing on the EU level, and here we see a lot of distributed production, both inside data centers and outside data centers. Something that we did not consider here is EV integration, although that is also quite possible, and there are some examples of how data center can use EV as controllable loads. Apart from that, there is a competitiveness of EU sovereign compute objective compared to hyperscalers from USA, China, and other countries. Finally, there's a need for cross-border orchestration within the EU that would allow to host cross-border platforms in a distributed manner, which increases the complexity. And for that part here, which is mostly digital part, we try to address those tendencies by introducing our own way of doing the edge compute, of course, compliant with Cloud Native Foundation and some examples from EU pilots, but also HPC and AI services. We considered them in a marginal way. They're still important for scaling of the services that we demonstrate. Therefore, we also were mindful about those and discussed that in the deliverables. So how do we actually propose to solve those objectives? Having said the hyperscalers are predominant service providers for clouds and virtual machines and so on, we propose to distribute the computational load, which is not very heavy, around edge data centers, which is not already normal edge like BMS systems or single machines, but larger scale infrastructure. So edge data centers, we of course cannot prototype full-scale edge data centers. So we consider mostly a combination of 3 or 5 servers as a representation of each data center. Second solution that we provide is centralized cloud services. So what we basically do is to deploy cloud either across those edge data centers or as one data center cloud. And mostly the cloud is the basic building block of the services that we prototype in this use case. We tried both. We tried centralized cloud, on-premise cloud, and distributed cloud. And what we realized is that actually decentralized self-hosted EU clouds are more efficient from point of view of digitalization of energy services and combining them with the core data center business, which is provision of services, data services. Finally, what we innovated on in this use case is that normally data centers are hosting generic loads without distinguishing in terms of data sovereignty or other aspects that are important in the EU framework. They consider all those loads in the same footing, but actually what is very important is to enable cross-sector cooperation and cross data center cooperation to ensure that actually the generic loads are converted into loads that have specific labels on them. For instance, this is private data, you cannot share it with anyone, so it has to be hosted as a main bulk data center part service. But there's also, for instance, energy communities that do not have as secure or high security requirements. So those can be moved between data centers if agreed properly with the owners of those communities or managers of those communities. And stakeholders consequently include data centers, energy communities, controllable load operators, because they need to have a contract also with cloud that is deployed for the purpose of interoperating the data center business versus energy business, and actually bring benefit to both sectors. And especially when it's concerned different countries, that's something that is a challenging thing to solve. So that's why it's important to have them as stakeholders here. And finally, RES operators. In our case, we just took data from RES providers and used it. So we don't have the actual RES on board, RES operators on board, but still that I think that the real-time data is a good representation of how the rest could be operate together within the digital platform like that. Finally, there's retailers, aggregators, DSOs, and TSOs that are mostly prototyped on the level of data space consumers, data consumers, and some of them are just prototype in terms of data models used in optimization. So concerning the services that we deployed and the technical architecture, I will explain two main services. There's more in the use case, but I think those are quite important and demonstrate main idea of what we aiming for and what we deployed. And that is core energy management for data center, which means load orchestration. So we are looking at the ways of orchestrating loads in a cloud native way. Why? Because it becomes both automated, so we can automate those orchestrations, but also it could be a human in the loop way. So it's quite flexible. That's why we are so interested in actually orchestrating the compute loads apart from EU digitalization strategy. And of course, in order to be consistent, we prototyped mostly as a simulation the different types of controllable loads that can be integrated with data centers and are integrated in practice in some data centers, and how we can provide ancillary service to those. Finally, and I think that's the most important one, we are aiming at demonstrating how different data centers can collaborate to optimize their use of power. And in that respect, we look at the data center, two types of data centers. One type is actually that is powerful enough to accept loads from other data centers. And those data centers that have a lot of renewable penetration in their countries, in their locations, and possibly grid congestions that we could resolve by moving loads from those data centers to the bigger data centers that can host them. those loads. And of course, we are thinking here about the loads that are not overly secure. So there are some loads we know from our data center projects that can be shared, that can share their operational details and also power consumption. And for that, we, of course, have a centralized node, which does deploy the load management services, grid simulator services, and streams REST data from the location of those data centers, which is here, of course, not real REST, but data streamed into the platform. And finally, this main node that deploys the services, it is a hardware orchestrator, or in the scaled version, further scaled version, HPC, is represented by some servers that can host additional loads. So how this operates is that normally those servers are occupied with some other loads. But in the time where we have likelihood of ancillary service provision requests, we empty those servers and dedicate them to the hosting of the loads that we accept from high renewable countries that would like to move their loads when the rest is not available, and they cannot or do not want to cover those loads with their own grid consumption or batteries. And in order to understand how this should be done, this load movement, of course, we need some dedicated tunnels between the hardware orchestrator and the controllable loads that actually provide data for optimizers that decide whether the load should move or stay where they are. In this respect, there is two types of architectures of the plants themselves: the data centers with controllable loads that comply with industrial security, and this is mostly IEC 62443 protocol that about zoning of industrial plants, and that's what we were thinking about when we created those tunnels, encrypted tunnels that allow the hub-spoke data exchange. So energy here, for instance, is managing mobility. Our external devices like PVs or EVs that either live in the same data center that wants to move the loads outside, or it could be just agreement with some operators that are in the same location as data centers about providing flexible loads to data center. And another thing is industrial OT that is compliant with IEC protocol for zoning. And here we have clear separation. Here we have a gateway which splits the tunnel from the actual business thing. And the first thing that is implemented here is a context broker that directly connected to the gateway, and nothing else is connected. So in the case where we use normal controllable loads, we have even architecture. All of those components can connect to the API that the platform provides and deploys at the edge. But in this case, it is only possible through the context broker that exchange the data as a demilitarized zone. So there's one side of the architecture that talks through the outbound connection only through the to the platform itself, and there's another side that works only through the outbound connection to the other side. And basically how it works is that the parcel comes into the broker, where the broker puts it in another side, and then from that other side, let's say PLC simulators, they take that parcel and the other way around. So when parcel comes in here, then the context broker puts it to the other side, and then that parcel then is taken by the hardware orchestration platform. Those context brokers are outbound connectors. But actually what I think, yeah, maybe that is what is meant by brokers here. There's also one broker here that works as an inbound. So the platform accepts all those parcels and looks at what's going on in the actual industrial plant, and then decides how to act on its behalf. And another thing here is that actually which is probably not shown here, the actual procurement of services happens in here, but also the parcel goes in with the procurement instructions, and the procurement instructions are handled here. Apart from that, of course, we need a grid simulator that is also a part of the platform, but it lives on a different setting. Actually, that's like a demilitarized zone for the hardware orchestrator here that is accessible through the REST API by any participant here, either the normal energy participant or industrial participant. And it defines the computational status of the grid, shows the congestion and so on, and that was developed by Mosen's team. It's a large contribution here that we base all our calculations on in the 3 countries. And finally, there's one more thing that is extremely important, is that we also get data from a cross-border SAS layer, and you saw partially part of it with the front end on P2X bid platform, but also we have here some public KPIs where we can allow access to dedicated vendors to the platform directly so that they can operate in their own Kubernetes clusters. And by the way, just to make sure we're on the same page, this hardware orchestrator works fully in Kubernetes. Okay. So what were the main implementation barriers that we have overcome in the end is there do not exist a standard procedure for moving loads between data centers. Of course, we don't standardize, of course, but at least we partially solved the question how we actually can move sensible loads. And so the different data centers would not be authorized to move sensitive loads. But of course, we exclude most sensitive loads that are private, fully private. But those sensitive loads that actually are allowed to move, and there are a lot of them, a lot of groups of those loads, we use those mostly. So non-sensitive loads have to be identified without violating data privacy. And that is a very important thing, because what we actually do is we share this part here through the data spaces EDC connector, the Eclipse connector, where we share metadata, which by itself could be private, but it only shared in the Kubernetes cluster belonging to a specific data center. So in the platform, we also have a split in tenants, and we give each data center their own Kubernetes cluster to make sure there's no violation of data privacy on the platform itself. But this is only metadata. There's no raw data stored there from data centers. And then lack of fully operational EU-level energy data space. So, of course, data space for data centers energy data spaces, they exist, but I think they serve a bit different purpose. And the main difference there is that the data space must handle the data streams and not just the static load of data. So it's extremely important that it stays always up in production. And that's what we achieved and actually have on 3 servers in different countries. And here we also say that, okay, DC connector, the default one, is made to communicate the static data, but we use it actually for streaming. And that's some kind of novelty we have here as well. Maybe it was implemented somewhere else, but not publicly shared, or maybe we couldn't find it. If you find something like that, you can tell us, and we'll take this into account. Then another thing is internal data center energy services, which use simplified type of IDC connectors. So we also protect the data inside the data center, because what we do is we deploy the services on the data center instead of having them centralized in our DP platform. And but also inside there, we have kind of a service provision type ETS negotiation that makes sure that nothing is leaked from data center to the main platform. So operational services, they're coupled on the spot. Finally, the connector has been optimized to resource-constrained sector communication, and here we use MCUs, so microcontrollers. It's not Raspberry Pi anymore; it's a lower level, and actually, data space built there is based on those connectors. Okay, so now I'll go to digital ecosystem. And here we built our own data space portal where you can register a data center or energy party. And here we show the example of the energy community registration. Basically, what it does, it registers their connector. And it can also search for data sets and services. And then the data sets and services, they require also to provision of certain data, which is negotiated within the connectors. But the nice thing about this platform also is that it's inside the ODP part of the whole use case. What is good about it is that we also support deployment of EDC connectors. So if the energy community provides the credentials for their compute infrastructure that we can use, then we can automatically deploy that connector in their premise and actually stream from that connector to our front end instead of them creating it themselves and then providing us the endpoint. That's also something we demonstrated on Raspberry Pi running Kubernetes cluster. There we have actually normal Kubernetes cluster without tenants, but we demonstrated that actually with 3 Raspberry Pis, you can run the whole communication, edge communication infrastructure with such a resource-constrained setting. Of course, Raspberry Pi is not very good for that for long term. Like it can live for 1 year, but full production, so all the time streaming. But it cannot live for, I think, more than 1 year or even less. So for that, we have other ideas what to use instead. And that brings us to the core idea of this use case when it regards piloting. Actually, what we tried to do at the beginning, we tried to structure everything around data centers themselves. But we realized fast that it's not actually possible because data centers, if they consider it as their own thing, hosting the platform, then it means that different data centers are not in the same position there. So some of the data centers may actually learn some of the data from other data centers, and it's not very good. So there should be a centralized platform. And it should be based around the data space coordinator. But also there should be some coordinators that use AI to transform the JSON schemas either for mostly for raw data, but sometimes also for the data space data. We only transformed the raw data, not the data space data. Okay, so here, continuing with this, what we found, and it's extremely important, I think, for future development of this use case, is that native IDSA mapping doesn't work for us. And that's actually when we try to have data centers as consumer and provider and consumer. And here we actually had a problem that a provider that has a workload and the consumer who wants to host those workloads and gets a benefit from it is a quite bad architecture, because in the end we could not make all the ends meet in terms of European data space requirements. But if we reverse the roles and make it, for instance, in Denmark, we have apart from our cluster that represent a data center, we also have a service provider that is a separate cluster of 3 machines, actually low power ones. So and those machines are part of the main platform that we host. And for instance, in Germany, which is pure data center, we don't have any intelligence there on top of the pure data center. Then it just basically buys the capacity for peak shedding And when our centralized Danish OTP platform gets the request from the service consumer that says, okay, I want to sell that amount of capacity during the next period of time, and we consider that as 1 day for providing ancillary services, then basically this setting deploys the well, actually it already has a connector. It deploys a connector on this setting, and then the negotiation basically is represented here, how our assets work. So asset is the actually service provider asset, which says, I have this compute infrastructure. I would receive your loads for remuneration, and then the service provider someone who accepts the service, which is in this case Germany cluster, they respond with this kind of template, field template. Okay, so then going forward, this is the actual negotiation process between the consumer connector and provider connector in Denmark. And this one, consumer is both Germany and Finland. And I won't go through that too much. If you want, I can do it later. And then finally, going to what do we use to deploy and orchestrate all these things and so on. And we use, of course, the cloud native foundation tools. I won't go through that. We use Flux, of course, Helm, and some other things from here. If you are interested, I can explain to you. And what mostly here is the subject of discussion is different orchestration layers. So, of course, our main one is CNFC toolbox, like orchestration, but we also marginally use agentic orchestration, and we implemented our own simple framework. Well, not a framework even, it's just a local set of rules that allow us to use AI for translation of JSON schemas and actually automating the orchestration SH files. Then another thing is hierarchical that we mostly use in use case 1, but also a bit in use case 2, because we have the MPC implemented that moves the loads between data centers automatically. And GPU HPC, that's a future work, because actually we wanted to implement something, but we are not yet there. So, and why cloud native way? And this is mostly because of tenants, because now we can split different communities in the same platform, let's say, or split different data centers in the same platform, and they will be fully isolated in terms of their metadata and so on. So actually, there's 2 ways. One is Kafka managed by each tenant separately. That's what we do right now, which is less resource efficient, of course. But there's another way that you have the common Kafka, but then the participant have to agree that you share the Kafka, which is also quite secure, but it's just a matter of agreement. And of course, Kubernetes API, we use cloud native way, which means everything is done through Kubernetes API, not through, let's say, if we need to deploy infrastructure, we don't do it through Terraform, we do it fully through Kubernetes. And of course, Git pipeline to production, which is quite standard. We use the GitOps here. I think it's actually not even mentioned here. Flux uses GitOps, and that's what we have. And how do we deploy centralized services in the demilitarized zone? This is the example of a grid where we have, for instance, this is a DSO node, and we have the decoupled like microservice that runs separately this power flow analysis in parallel to this analysis. So it's like they have bidirectional exchange of data at each step. And then we have the data center leaves here in that branch here. And then we have a diesel generator here to probe and test how the grid reacts on the controllable loads. And basically in the cloud native way, that is done in this way. It's actually was my presentation somewhere. So yeah. Diesel generator is a tester. For instance, it lives on 8001, and battery BESS lives on 8002, and then data center. So what we did here, we deployed that in the same tenant. But actually, what we'd realized is that if we have two data centers that have different congestion on different DSOs in different countries, then we actually need different tenants to do that. That picture is from the time we couldn't make it, but then we actually made it work in different Kubernetes tenants. So we also can separate the compute, and if we don't need a centralized platform, we can even put them in different distributed platform if we need to. And finally, we have the centralized power flow engine. This is mostly done for demo, where we have a grid that combines other grids. But generally, we have distributed grids here developed by our electrical team with Mosen that have their power flow analysis running as separate tenants. But then there's a centralized tenant which we actually deleted in the end because we just needed the distributed ones. That was for testing, more or less. Finally, yeah, this is the same slide. Finally, this is the interface for controllable loads. And I was speaking about human in the loop, and we tested it first as a human in the loop. And here you can either increase the loads here manually, or you can click start. Then it will start the schedule for different devices on the same network, and that schedule can be prescribed beforehand. Okay, I hope that was clear somehow. Then I would like to speak about results here. And the first thing that addresses the data center passive fragmented loads, joining them together through a maybe grid overview and the flexibility and so on. We address that using the power flow analysis chunks and also the optimization of grid loads. We have an optimizer running and informed by the grid power flow analysis in different countries that actually decides in real time whether the load should be moved from Finland to Denmark and from Germany to Denmark, or they should not be moved. Okay, so here sovereign data exchange part was implemented in the EDC connectors here, and then we have the yeah. So we have some numbers here about how many and what we do here and so on. And then we actually see that we have different types of connectors here that work at the edge. And the Raspberry Pi connector is industrial thing that runs the industrial connector in the IEC framework. And then we also have the public connectors in the VPS, virtual private servers. And then we actually achieved we finalized the cross infrastructure integration, where we have different parts of the platform in terms of the core platform and edge devices that I described before, running as one big closed loop thing. And then there's a full validated workflow that we also run in real time across different countries and servers, which I already discussed, I think. Publish dataset, discover, negotiate, agree, and access data. I think this is for data, but also we have a similar to for negotiation of capacity and actual provision of rights to the service provider to move the computational loads through IDC connectors. Finally, there's a bit of information about how we do the optimization between the different servers. Some preliminary work where we defined different carbon footprints in different countries for considered grid together with the nodes. And of course, we had to project, we did not use the actual loads there. We used the increased loads to match the grid simulator and optimizer. So of course, we have smaller loads running on in each of the countries. So, and then finally we did this simulation on how much can actually be saved. And that's a pure simulation, so it's maybe not as interesting, but in the end we applied the same approach in the scripts that we used while we were moving the loads. And there's some statistic here that maybe you would like to look later on in more detail. Carbon emission results that we got, and then waste heat recovery profile, projected waste heat recovery that we could get out of those simulations. Finally, we have simulations were very important for us because we actually first looked at how pods should be moved and what impact they bring to the actual load, computational loads. That's why we also did some simulations here. And then the summary of simulation results about carbon emission, which is quite substantial, but of course this is a simulator, so we don't know whether it makes sense or not. And then finally, we used a real data center UPS battery, where we used we calibrated that first, and then we used it for projecting the model predictive control. That we did separately because it was a bit hard to just technically, we were not allowed to put that UPS on the service that we were actually running. So that we did separately with the data we got from actual experiment. Finally, there's some results on battery SOC analysis. And that one, I think that is already with the hardware, well, which I'm not sure 100% about. And finally, the facility level emissions were calculated based on those experiments. Community aggregate here and so on. So finally, the data center load transfer experiment. That is oh, actually I think this is a wrong one, but yeah, so we should look in the lower one, which actually shows the result of actual load movement between data centers. And here there's different comparisons. So we have the predicted from simulator. We predict certain way how load should change here, and and then we ran two experiments. So first, actually, the one that should be looked at primarily is the Gnome-Kepler, because that's what we data collected from the nodes using Kepler. Those data is the primary source of optimization from the data center part. And then after that, we also had BMC chassis signal, which is a direct signal. And I think here it seems that we actually get smaller values for the BMC. Which is not always the case, I remember from the experiments, but that's a good representation of how the computation can differ for different load estimation, ways of load estimation. Okay, so and
we
finally,
almost running out of time. Just
yeah, sorry for that, but
no
I'm almost done.
Perfect.
So and here we have some KPIs. I think this one is from simulation here, but this one, because we don't have the simulator with contact negotiation, that is from real experiment. That is how much actually this is related to something that how service is good after we moved it, because actually we do the service in real time, and we wanted to make sure there's no downtime. So first experiments were actually with downtime, but then we found a technology, also a cloud native technology from the cloud native toolbox, that actually allows us to go almost without the downtime, which is quite good. And tenant provisioning here is very fast. And of course, we pre-do the architecture before moving the actual loads. But after the architecture is deployed on the bare metal server, then we can provision tenants already within the created infrastructure, software infrastructure that we made on Kubernetes. Yeah. I think that's more or less it. And lessons learned, a lot of lessons learned here. But I think the most important one is that we were very few people in the beginning, a year ago. And we tried to actually set this up ourselves. But what we figured out that whenever we a bit cautious less about production, it goes down. So what we realized, there's no way we can do it on ourselves. That's why we needed help from external parties that would advise us on how to keep everything in production all the time, and also advise us on how to use cloud native tools in a best practice way. And the innovation, of course, that we self-service connectors by a portal button, we deploy them automatically. Then, of course, we implemented the cross-border workload scheduling, which we know only from Google studies. Maybe someone else did it recently, but at least half a year ago, that was not available. And then the HDeploy AI. Yeah, I'll just need to see which part is this. Depends on community optimization applicable to buildings without IT expertise. Okay, this is actually the JSON translation part that helps to reconcile the edge schemas to the platform schemas. And that's was the major thing for, I mean, that's the only thing that we did in AI, but that is, I think, is quite a good novelty as well. Open source stack throughput, no proprietary dependencies here. Yeah, so we have ARM and AMD architecture, also Extensa and RISC-V. So it not mentioned here, but that's also the very edge gateways, which allows to stream the data into the platform and stream the actuation set points. And yes, of course, embedded edge MPC was also quite good development. And thank you so much for listening. And please let me know if you have any questions.
Thank you very much, Konstantin. And I see that, of course, many people had to jump to other meetings that they had right now. I think that we have reached the maximum time that we have blocked for today. In case there is someone that has a question, of course, maybe we can just stick here for 1 minute more and to pass it to Konstantin. But otherwise, I think that we have covered everything that we wanted to cover today. Thank you very much for the ones that could stay with us until the very, very end. I know this has been a very long day. I think that we can wrap it up here. Konstantin, thank you so much for your time and for the very information-packed presentation. I will send an email with a wrap-up of today and with the polls, but I think that I did my closing before, so we don't need to stay here for longer. So yeah, thank you very much for your time, and thank you to all of our presenters. I think that today has been extremely interesting, at least also for me, even if we've been in Begonia for more than 2 years. So thank you very much to all of you, and we will reach out soon with the next steps. Thank you.
Thank you so much.
Thank you.
Bye.